This video is a continuation of my last video on solving absolute value equations. We are again going to look at how to solve these absolute value equations graphically as well as algebraically. We're going to start here with this example, the absolute value of x minus 5 equals x squared minus 8x plus 15. The first step is to try to isolate that absolute value symbol, and as we can see, it is indeed isolated, so I don't have any algebra to do right off the beginning. But what we want to do next is consider two cases. We want to consider case 1, where the stuff inside this absolute value symbols is indeed positive. So I'm saying, let's say this x minus 5 is positive, and it's still going to equal x squared minus 8x plus 15. And the second case I want to consider then is where the absolute value, the things inside the absolute value, have a negative value. So we're saying x minus 5, we want to consider that to be negative, and then we get x squared equals x squared minus 8x plus 15. So now we go through and we simply solve both of these equations. Distributing a positive 1 gives me x minus 5 equals x squared minus 8x plus 15. Now we can see we're going to have a quadratic forming here, so we want to actually move everything where the leading coefficient of my x squared term is positive. That happens to be on the right hand side. So I'm going to subtract the x, add the 5 from the left hand, which means subtract the x, add the 5 also from the right hand side of the equation, which leaves me with 0 equaling x squared minus 9x plus 20. To keep going in this example now, from our quadratic unit, we should remember that if we have a quadratic equaling 0, we actually want to factor this quadratic. So we're looking for two things that multiply to 20, add to a negative 9. Well, that's x minus 5 and x minus 4. Again, from our quadratic unit, we remember that we just need to set both of these factors equal to 0 and solve for what their roots would be. So x minus 4 equals 0 also. This gives me one possible solution that x equals 4. This gives me one possible solution where x equals 5. So we solved the positive case. Now we need to go through and do the exact same thing with the negative case, which means I'm going to distribute in the negative, which gives me negative x plus 5 equals x squared minus 8x plus 15. Again, we want to move things to where the leading coefficient of the largest power is positive. So I'm going to move things to the right. In this case, I'm going to add the x, subtract the 5 from both sides, which leaves me with a 0 equals x squared minus 7x plus 10. Again, I'm going to want to factor this quadratic, so I need two things that multiply to a positive 10, add to a negative 7. That gives me x minus 5 and x minus 2. Again, set both of these factors equal to 0 and solve. This guy gives me a x equals 2, and this gives me the x equals 5 again. So if I was to look, I was solving my absolute value equation that was up here at the top. I was solving this, and I came up with 3 different possible solutions. Maybe x equals 2, maybe x equals 4, and x equals 5 shows up twice, so that's just considered one solution. Maybe x equals 5. But when we're solving absolute value equations, we know that we have to verify to make sure none of these are in fact extraneous solutions. So we're going to verify all 3, and we always verify back in our original equation to test if it makes sense in what we originally were given. So we're going to test all 3. We're going to test 5, and we're going to test 4, and eventually, if we have some room over here, we're going to test 2 as well. So let's go through and test 5 into that equation. So it's going to be the absolute value of 5 minus 5 equals 5 squared minus 8 times 5 plus 15, which gives me 0 equals 25 minus 40 plus 15. And if you actually put that into your calculators, you will see that we have 0 equals 0. Therefore, this does verify to be one of my solutions. Now let's go through and verify x equals 4. So again, we're going to put it in, and I have the absolute value of 4 minus 5 equals 4 squared minus 8 times 4 plus 15. 4 minus 5 in the absolute value signs, we know that's negative 1. And if I crunch all that stuff in my calculator, I get negative 1 on the right-hand side. But if I look, the absolute value of negative 1 is 1. That does not equal negative 1. Therefore, this is an extraneous solution. And now we're going to look at the last one, x equals 2. We're going to plug it in, and we're going to get 2 minus 5 equals 2 squared minus 8 times 2 plus 15. 2 minus 5 gives me negative 3. Stuff on the right-hand side here equals 3. So we actually see that the absolute value of negative 3 is 3. That does equal 3. Therefore, this is a solution. So at the end, we can make one statement to kind of bring all of our work together. We could say this absolute value equation had solutions at x equals 2 and x equals 5. And we should be able to verify this visually through graphing it on our graphing calculators. So if you go in your graphing calculators and enter the absolute value of x minus 5 in y1, and that quadratic x squared minus 8x plus 15 in y2, and we graph it, we can see we have the absolute value, that big V is the absolute value, the parabola is the quadratic we graphed, and we can in fact see that it looks like we only have 2 intersection points. So to find them, we just go back to second trace, choose option 5, which is the intersection of the two graphs, first curve, second curve, and let it do the work. And you could see, in fact, one of the solutions is x equals 2, and that's what we've proven algebraically as well. Now let's go through and find the other intersection point to see if it is indeed 5. So we go second trace, choose option 5 again, and remember this time we want to be closer to that other intersection point, so it'll actually find that one. And we just let it do first curve, second curve, and let it find the solution again. And again, you could see that x equals 5 is the other solution. So in fact, graphically, we've got the same thing as we did algebraically, which we should. So that proves our work. So now we're going to do one last example here to show one other kind of situation we can run into when solving an absolute value equation. And this is the equation here. Solve the absolute value of 3x minus 4 plus 12 equals 9. So let's go through and solve this algebraically. Then we'll take again a look at it graphically and see what we see. First thing we want to start doing is to isolate this absolute value. Now that absolute value right now as it stands has a plus 12 out the back. So we want to get rid of that. So we're going to subtract the 12, and we're going to have the absolute value of 3x minus 4 should now equal negative 3. Now this is what I call in class one of those red flag moments. Something should be sticking up in your head saying something's not sitting right here. We know that the absolute value, anything in absolute value, has to equal a positive value. If we look, it's saying it's equaling a negative 3. That cannot happen. This whole situation then is impossible. We cannot have a negative absolute value. So in this situation, we would deem it to have no solution. There is no value of x. If we look back to our original equation, there is no value of x that when put into here would make the left side equal the right side. And we could prove this graphically. Look at the visual representation of this as well. If we look and we put it in the absolute value of 3x minus 4 plus 12 in y1, and then say y2 equals 9, you're going to have to adjust your windows here a bit on your graphing calculator, get your y max maybe up to about 20, and if you look at it, We could see right here, here's our absolute value graph with the plus 12, and here's y equals 9. They're not intersecting at all. Therefore, that proves visually that there is no solution either. So we solved two more examples with absolute value equations.